Log on, tune in, find out. Another good idea from Cambridge.
Good. Well, so next speaker, Matteo Borrotti from University of Bologna, and he will be talking about an evolutionary approach to experimental design for combinatorial optimization. Over to you.
Okay, good morning. First of all, I would like to thank the organizer and for this opportunity. And now let's go with the talk. So this is a joint work with Alessandra Giovagnoli that she was my supervisor during my PhD. And in this work we investigate the possibility to derive combinatorial novel approach for combinatorial optimization in the context of experimental design, with a particular attention in one application in the enzyme engineering field. So here the outline of the talk. So we will start, I will introduce you the motivating problem, then some definition about what large P small n problem is. I will focus on the n colony optimization, and then I will present you my proposal solution, our proposal solution with some simulation study and also the last application with conclusion. So the motivating problem is about the design of novel or improved enzyme. And in biology, this research field is called enzyme engineering. And I know that probably some of you is not familiar with this context, with this research field. So I just give you some definition that can be useful for the rest of the talk. So I just start saying to you what an amino acid is. An amino acid is a molecule commonly identified by letter, and we know that there are 20 amino acids in the nature. Then a string of amino acid is called a polypeptide, and when a polypeptide is able to fold into a three-dimensional structure, then you can call this polypeptide protein. And each protein can be divided in domains. So try to think on a string of letters you can divide the string in substrings. Then the substring is called domains, and the minimum length required for a domain to fold is believed to be 50 amino acids. In our case, in our specific application, we use something artificial because we create some artificial domains. We say that are artificial because they don't exist in the nature. So they are just sequences of amino acids that don't exist in the nature, and we collect them pseudodomain. Then we are more interested in enzyme, so I tell you what an enzyme is. An enzyme is a protein that is able to do catalysis. Catalysis is the ability to enhance chemical reaction within a cell. In our application, we define a score that is just a number that is measuring how an enzyme is able to enhance a chemical reaction, and we believe that this score is going between 0 and 1000. So just introduce you the motivation study. So we start from a library of 95 randomly chosen pseudodomain. And what we want to do is to build an enzyme with 2000 amino acids. So just two things about a ball with 95 building blocks inside. So you have to take one from the balls and put in the first position, and then take the second one, put in the second position, and then the third one, the fourth one, and at the end we will have an enzyme with 2000 amino acids, like you can see in the picture. So just the first string is one domains, that is attached to the second one, third one, and fourth one, and then you have your enzyme. As you can see, the search space is really huge because it's composed by all the permutation of 95 elements in 4 positions with repetition. So it's more than 81 million of points. So the experimental space is quite big. And just a small detail, the data that we study are the score of the evaluated enzymes. So at the end, the main challenge from a biological point of view is to develop methodologies to construct non-natural enzymes, so enzymes that you cannot find in nature, with a specific function without the need to screen a large number of sequences in our huge space. So instead to evaluate all the 81 million points, just few, and find something. So just we try to characterize a bit our problem. So let's say that P is the number of variables involved in our experimentation. So in our case, if you think P is at least 380 variables, because you have 95, you have to choose 95 pseudodomain in each position. So it's 95 pseudodomain multiplied for position, you have 380 variables. And let's say that n is the number of experimental units. And in our case, we decided the number is 96, and we decided to take this number in according to the dimension of the experimental well plates that the biologists use to evaluate the enzymes. So as we can see, we have a large number of variables, obviously enormous number of different ways in which pseudodomains can be composed. Then the network interaction can be really huge, and then we are in an experimental setting, so we have also to respect some rigid laboratory protocols. So starting from this small definition, we decided that we had to study some approaches for discrete problems. So we decided to, from a statistical point of view, take care about statistical model for high dimensionality. So for when you have small points but a huge number of parameters, and from the computer science, look at the combinatorial optimization, that are algorithms for discrete problems. So here just a picture of what you can find in the literature. Okay, there are just few models. You can find now more model, more reliable, and so on. And just going to the right part of the slide, you can see that we focus on meta-heuristic algorithm that can be mainly divided in two groups. One is called the population-based search. So you have to think that the algorithm involves a set of solutions during the search phase of the algorithm. And then the other one is the single point search. So it works with a single candidate solution at each iteration. You can find many different algorithms in both of the two groups. Just a small definition, we focus on bio-inspired algorithms. So algorithms that take inspiration by the nature, like ant colony optimization, or like the one that we saw some days ago, the particle worm optimization. What we propose from this picture, we propose to combine the techniques. So using different approaches from statistical model and optimization algorithm in such a way to tackle our discrete problems. So the ultimate aim is test the possibility of exploiting bio-inspired algorithm combined with statistical techniques to search for an optimum in a discrete search space, and to develop methods to solve problems where the number of variables increase a lot. So what we propose what we call a model-based and colony design that is based on closed-loop evolution and colony optimization. So now just we focus on colony optimization. And colony optimization was proposed by Marco Dorigo in his thesis in 1991. And this is a population-based general purpose stochastic algorithm for the solution of difficult combinatorial problems that take inspiration by the foraging behavior of ant colony in the environment. So while an ant is moving in the environment, is leaving on the ground a particular substance that is called pheromone. So when another ant has to move from one point to another one, is choosing where to go in according to the quantity of pheromone that it is able to smell on the environment. So it's demonstrated that a colony of ants is able to choose always the shortest path between 2 points. It was around 1944-43 that the experimenter did some experiment to demonstrate this particular behavior of the ant. And they took a nest with a colony of ants, and then a food point. So they found a point with food, and they put in the middle a particular structure, like the one that you can see in the picture. And they let a colony of ants go inside this structure, and you can see that the 2 points are divided with 2 bridges with the same length. So the ant was moving from the nest to the food. After a while, they realized that all the ants were 50% in one bridge and 50% in the other one, just because they were just with the same length. So they do the same with another different structure, where one bridge was shorter than the one was longer. They let the ants go inside, and after a while, they saw that all the ants were mostly in the shorter one, just because the shorter one, an ant could move in the shorter one more fastly with respect to the other one, so was leaving on the bridge more pheromone at each step. So the pheromone minutes by minutes was increasing a lot, and then the other ants in probability was choosing the shorter one. So just to explain you how it works. So the environment is simulated by a graph, and each node is a component of the final solution, and in our case a node is a pseudo domain in a specific position, and then each node is connected with the other with the arches. In our case one pseudo domain is connected with all the other in the next position. In each arc you can find mainly two things: the pheromone weight, so a number, and some heuristic information like the cost to go from one point to another one. And the final solution is a path from the source to the destination node. In our case, the final solution is a sequences of 4 nodes, or a path of 4 nodes connected by 3 arches. Then an ant in element I chooses the next element in a probabilistic way according to the pheromone weight and the heuristic information on the connection between nodes. And these two information are combined with this formula, and this formula is this number is then transformed in a probability that at the end you will find a probability in the arc, and this probability is the probability of an ant k moving from one node to the next one. So here just the simplest pseudocode about this algorithm, so just to have an idea how it works. So you run the algorithm until a certain stop criterion is satisfied. Then you generate the solution in according with the probability that you can find in the arc. Then if you want, you can apply some daemon action that are local search around the best point, and they used to apply when you don't have heuristic information, because heuristic information helps you to exploit around one point. So if you don't have this kind of information, you just apply a local search around the best, and then the pheromone, so the probability is updated. So now we can come back to this slide. There are several kind of different algorithms with the ant colony approach, and the one that we were interested in was the one proposed by Stutzle and Huss in 2000, and it is one of the most performing in this field, because he avoid early convergence to a local optima mainly with these 3 important features. So the ant that has reached the best solution in the current iteration deposits pheromone, namely weight, after each iteration. Alternatively, the ant that found the best solution from the beginning from the trial. So you choose the iterative best solution when you want to explore. If you want to exploit the solution, so you choose the global best. And then other 2 rules: the range of possible pheromone trials on each solution component is limited in an interval, and the pheromone trial is deliberately initialized to a value, maximum value. So now coming back to our approach. So our approach is a mixed approach that exploiting both information from a statistical model and the algorithm. As I told before at the beginning, is based on closed loop evolution. In closed loop evolution, you have a loop from real experimentation to a simulation phase. So you just you have real data, you go in a simulate phase, and then you generate the new candidate solution for the next real experiment. So it's important because we switch between real and simulated observation, and we require that our method simulate the problem and move in source space as many times as we want, thanks to the statistical model, that you have to see the statistical model as a surrogate of the search space, so emulator of the search space, and then get an iterated refinement of the predictive model at each step. Because at each step you will have more data, and then the model will be more accurate. Okay, so going more in depth in our approach. So it's mainly divided in two phases, the simulative model-based phase and the learning and experimental phase. So you start with a random population or trial of enzyme, then you estimate your model, and you use your model as a surrogate of this space, so the algorithm can be moved and search for the next candidate solution. Then you choose the next candidate solution, and you go to the real experimentation, you evaluate the new enzyme, you add this enzyme to a library that is going to be big and bigger at each step, and then you estimate again the model, so the model will be always more reliable and accurate. So before to go to the application, we just test our methods. What? Okay, perfect. We test our method in with some benchmark function. So we choose two benchmark functions that we build together with the biologist, and they are trying to simulate some particular landscape, biological landscape. And for each function we add also a error term that with normal distribution, 0 the average and variance equal to 1. And we compare our approach with the basic version of the max-min system. Here some setting. So the experimental batches are 30, and for each batch we have 100 experiments, almost like in the experimentation. So here the result with the first benchmark function. So we plot the average maximum value over 100 simulation, and we plot also the 95 confidence interval around the average, so the point. The solid line is our approach, the dashed line is the max-min system. So you can see that just after the first iteration, our approach is increasing a lot the value of the score, the response, and then start to increase step by step, going to the optimum, that is able to find the optimum after 25 iterations. The other one, so the basic version, has probably a more stable behavior, but if you can see that at the end, after 20 iterations, the line is just flat. So probably is not able to increase the score anymore. Anyway, this behavior is confirmed by the next slide. So here, always the solid line is our approach, and the dashed line, the basic one. So you can see that our approach, in this case, after the first iteration was increasing a lot the score, the final score, and also look at the fourth iteration, you already get a good approximation of the optimum. And then you are able to get the optimum after, we can say, 12 iterations. Anyway, we were comfortable with the results, so we went to the application. So just to summarize this application, we have a library of 95 randomly chosen pseudodomains. We generate synthetic enzymes with 4 subdomains. And then the search space was really huge, and the initial data set of, and we started with the initial data set of 96 randomly chosen enzyme in the space, like the approach required. So the maximum number of trials that we tested was 6, and for each trial the number of enzyme was 96. So to avoid early convergence of the approach, just because we had few trials, we decided to apply a rule to avoid the convergence to a local optimum. So at step I, the best solution is compared with the best solution on the previous step. And if the best solution on the previous step is not incremented by at least 4%, then all the probability that I was speaking before in the axis are set to a uniform distribution. So you let the algorithm explore the space instead to focus in one specific path. So here the result, okay, this one just the first trial, the random one. So just one enzyme had a really quite high value of the score, and the other were not so good. So starting from this situation, we let our algorithm go for trial number 2, 3, 4, and 5. And you can see that, okay, I don't know if you can read here, but maybe it's too small. But anyway, you can maybe see that the distribution of the score is moving on the right part of the x-axis, so it's going to the high value. If you look at the third quantile, in each trial is always getting higher, with a section with the trial 4, that is the trial where we apply the rule. So here the last trial. So the last trial, look at the best score that we reached is 834. That is quite high for this kind of experimentation. It's almost going to the optimum just with 6 trials. And all the 96 points that we tested were in a region of the search space with a high value. And also the experimenter went to the biologist went to test this enzyme, and they were quite happy about the result, because it was an enzyme that they was just new, but he was showing some ability to attach with the particular substance and so on, something that I don't understand really well, but they were happy. Anyway, last point to say, to the time to a new the approach takes for a new trial is 40 minutes. Can be, some of you can say that is quite a lot, but you have, if you want to reduce this time, you have just to run the algorithm for less iteration, for example, or I don't know, ask a computer scientist to write the code instead of me. And anyway, if you think that evaluate the 60 points takes to a biologist 3-4 days, for them is nothing, 40 minutes. And overall, if you think that if you want to evaluate 81 millions of points, takes almost 1 year for them. So better 40 minutes. Then at the end, conclusion. So our approach allows us to create a dialogue between design and laboratory experimentation at each trial, detecting a path in the combinatorial search space, and also to test, allow us to test a small number of candidate solutions. Furthermore, the approach has shown their ability to identify new enzyme in a very large search space, at least one, and a remarkable shift of the initial population toward higher response value of the search space. So we are just at the beginning, so there are for sure something to do, and we would like to use more complex predictive model, because we know that we use just a linear one and is not getting the strong interaction between the domains. Also, we would like to create something like a model selection, so a big platform with model and every time select the best one to predict the point. And then, okay, treat the relevant information contained in each trial in different way. And testing, and we are already doing testing our approach in more general benchmark function to generalize the result. And then we would like to study the observed behavior of the algorithm more in depth, also from a theoretical point of view. And for the real experimentation, we would like to understand, so to prove which is the number of trials needed to reach a satisfactory solution, and generalize our approach in other field of applicability. So just the last point, look at the third future work. We are already doing something, and we already propose another approach that we call it naive colony optimization, that is based on naive Bayes classifier and the colony. It doesn't do simulation, it's just take the real data, apply the algorithm for one point, and then get the new point. For one iteration, then get the new point. And it's important, we like because it's able to better understand which are the pseudo-domains in each position, and was able to get the iteration between pseudo-domains in a sequences with the n colony. So for sure we regard this approach improve up the limit of the individual techniques. And just the last slide is how it works. So before I told you that the algorithm is based on a graph. So every time you have every iteration you have the previous state of the graph, and you apply the naive Bayes to our data. Then you find the pseudo domain, you can say this, in each position. Then the algorithm is taking care about the best path. So you just combine all the information and you create the next state of the graph. In a formal way, this is possible adding a parameters in the formula that I showed you before, and we call it naive information. So I just want to thank the research center where the experiments are made, and Thomas Tutzel and Mauro Virattari, that was my supervisor in Brussels when I studied this kind of algorithm, and some references, and thanks.
It's time for a quick question to Matteo. If not, I will ask one. In the slide, in slide 15, could you just remind me what is the response you are having where you show your performance? You just
Here?
Yes.
So what I am plotting?
What is the vertical axis on that? That
okay.
response.
There is this value.
That's a simulated value.
Sì, exactly. We use our benchmark function that we created together with the biologist, and then these functions are emulating the real problem, so it's something like the same. And so the problem was setting in the same way, and so we were choosing something like pseudo-domain, blah, blah, and the polynomial regression model plus a term was giving us a response, a score. And here we are just plotting the average maximum value over 100 simulations.
If there are no further questions, let's just thank Matteo again.